Okay, hello everybody. So I show you an application of using models. My topic is ENSO and tropical basin interactions, but it's also a little bit about model development. So here's my overview. Motivation is I'd like to develop models to be useful for me, and I'm also interested in ENSO dynamics. And I will show you results with the GFDL model because I couldn't get the ACCESS model running, but I also showed you the ACCESS model results that backed up the model, the results a little bit. Okay, so motivation, model development. So I was part of a paleo DP project. Simple idea, we wanted to rearrange land. So back in the Eocene, Australia is further south, India is not connected to Asia. And the question is, how does this impact the climate? Sounds simple, but actually it's impossible to achieve with the ACCESS model. At least we tried it. We worked on this for 2 years and we couldn't get it done. I have a little bit of giving up on it, but we achieved it with the ACCESS ESM, as David achieved it after about a year or so. David also can do it with the GFDL model, and I could do it within 1 month. And initially I thought it was simple because my first task as a PhD student when I started in the 1990s was to shift Cuba somewhere else to strengthen the Gulf Stream. It took me 2 weeks to do it back then, but nowadays these things are so much more complicated. But that isn't really my motivation. My motivation is really to have a fast GCM because I like to play around with climate models and ask questions like what if, like here, what if India is not connected to Asia, does it do anything? So my motivation is really to have a fast climate model to play around with it. Something, when I mean fast, it means 100 years a day or something. So something where I can do 100 of runs and it doesn't cost much, so to play around with. Okay, so my science motivation, so this is all technical, but my science motivation is looking at ENSO dynamics. So you know that ENSO is in the Pacific, it's a big mode of variability, and there's a small version in the Atlantic and not so much in the Indian Ocean. And the question is, why is ENSO in the Pacific? Why is it so big? And in principle, also the question is, does the other ocean basins actually matter? And the theory is pretty straightforward. It says bigger basin, larger variability. Larger basin would also means longer periods of ENSO, and the rest of the world is irrelevant. And I show you that all of this is wrong. So here are some results. So I use a low resolution model because I can run it fast and it's cheap. So I have 250 years for each of my simulations. The reference is the real world, and I use simplified worlds where I basically make the tropical oceans no land, and then I increase the land a bit more and more until I get to the Pacific, and then even more I get to the Atlantic. So that's a single basin. Then I have 2 basins, one where I have a twin, 2 Pacific-sized basins, one where the Pacific is shallow and the other one where it's deep, and then one where I have a big one and a small one. And then I have also 3 basins, which I will not show you results on. All of this is written up. You can read the paper if you want to. It's not going through reviews yet, but it's on some repository. If you have a single basin, this is the standard deviation of SST variability, and you can see the Pacific size is the one which has a nice variability which is similar to observed ENSO. But if you get to bigger basins, the variability doesn't increase unless you get to the very big one. And if you look at this as a function of basin size on the x-axis and then the amount of variability, you can see it peaks at the Pacific and then decreases. This is kind of unexpected, and really this should not have happened. And I don't have an explanation here, but you can talk to me. I have a PhD student working on this. So I have no explanation, but this is really an unexpected result. Even more unexpected is if you look at the power spectrum in these boxes here. And this is just for the 4 big ones. So the one that's bigger than the Pacific, and then the biggest one here, which is basically the whole Earth. And you can see the power shifts to be more oscillating, but also oscillating on higher frequencies. So this is 2 years, 3 years, 4 years, and 5 years. So the bigger the basin, the higher the frequency, which is the opposite of what the theory says on ENSO. So this is fairly unexpected. Again, I can not tell you why this is happening, although I can speculate, but you can talk to me later, and then I can tell you what I think, why this is happening. Okay, the more interesting results is if you have more than 1 basin. So I showed you the one which has just the Pacific and the rest is land. and you can see there's an ENSO mode variability. If you then have two options, the other basin is a shallow ocean that should not allow ocean dynamics, so should not have an ENSO-like variability, and you have two identical Pacifics. What would happen? And I asked a lot of ENSO experts, and you get it all directions, and here I show you what is happening. So if you have a shallow, different ocean basin, it does change the variability a little bit. It makes it weaker, and it changes a few other things, but nothing dramatic has happened. But if you have two Pacifics, you have a much more powerful ENSO mode. Actually, you have now two highly synchronized ENSOs that happen at the same time, and they are much more powerful and different in all characteristics. So in other words, whether there is another ocean basin or not does have a huge impact on ENSO, or can potentially have a very big impact on ENSO. If you look at how these are related to each other, so I show you the correlation. So I do a EUF analysis on the left basin, and I show you the correlation map of the time evolution of the left basin with the rest of the world. So you can see here in the upper one, it's a monopole mode, and over land it has positive correlations in sea surface temperature and surface temperature. When the one with the shallow ocean, there's almost no correlation in the ocean basin, and then the one where you have the twins, you have anti-correlation. So in other words, you have an El Niño in one basin and La Niña in the other basin, and these two things oscillate. And they oscillate very powerfully on a time scale of 9 years period. And they are very periodic. I will not show you this here. Okay, this much my results. I have many more results, but I only have 10 minutes, so I can't show you all the results. So this is a GFDA coarse resolution model. Now I'm doing the same experiments, a few of them, with the ACCESS-ESM 1.5, because David managed to get this going. And then just to back this up, that this is not purely artificial to the GFDA model. So here, the left is the GFDA results. Where's my mouse? So the left is the GFDA results, and then here, a few experiments I have done with the ACCESS-ESM 1.2. So you can see there's some similarities. So it has more variability if it's Pacific size, and less if it's Atlantic size, and less if it's bigger. But the biggest one here, you see there's quite some difference. Well, in the GFDA model, it wants to be a strong ENSO-like mode, but in the ACCESS-ESM 1.5, this mode is not very strong. In my twins experiments, you can see this is almost identical results. So you have the ENSO mode for the single basin and the ACCESS as well. You have it weaker when you have another basin that is a shallow ocean, and you have these twin modes, which should be identical, but they are not quite identical here. I'm not quite sure why, but they are almost identical. And they have the same kind of out-of-phase relationship, which I'm not showing you. Okay, in terms of findings that I have in the GFDA model, I have a number of things here listed that I find in the GFDA model. I basically find all of this in the ACCESS-ESM model as well. I have not tested all of it. The wind-SST relationship, I haven't looked at it. And some of the things are not as clear or not as strong as in the GFDA model. But basically, both models show the same results. Okay, summary about ENSO. Larger basin does not equal larger SST variability. This is, from the theory, is incorrect, or the models are incorrect that I'm using, but I think the theory has just not considered this. Larger basin is also not longer periods. The rest of the world is not irrelevant, it's actually very relevant. So I think the theory has to work extra time to work out what is going on, but I think it's really interesting. In terms of model development, I really like to play around with climate models. I think it's really interesting, but with a model as complex as the ACCESS model, this is really hard to do. And this is clearly a limitation for my kind of research. All right, thank you.
Thanks, Dietmar. I have time for a few questions. Yeah, at the back.
Thanks for the talk, it's really cool. I'm wondering if there could be something we've done when we're tuning the models to try and get a good ENSO that's made it good in the Pacific size basin and not in others. Can you comment on that?
Yeah, it's kind of what it looks like, right? I mean, it's kind of a magical way that you have ENSO peaking at Pacific and then going down. You might argue this is the optimal reference basin size to create ENSO, but it might also be that the models are just tuned and this is just pure crap. But let's be optimistic and say there's physical arguments of why this is happening. And I think there could be, because I think the atmosphere is the key element here to understand. And the atmosphere can lead to the fact that on larger basin size, the atmosphere leads to interference that would not allow larger variability. So maybe there is a reference size basin that is the Pacific size. But you're right, I think it looks like the models are tuned.
Hi,
sorry.
Dietmar.
Oh, sorry.
Sorry, yeah, go, Andrea. Yeah, you go. Good time.
All right. Well, so what happens with all the ENSO theories, like delayed oscillator, that would explain some of this periodicity of ENSO? So it doesn't happen in your model.
Yeah, so obviously I don't have the answer for this, but I can speculate. And my speculation is that most of the ENSO theory comes from an oceanic point of view, basically just discussing what is happening in the ocean, not considering there's also something happening in the Walker circulation. And the Walker circulation response, so the key element in ENSO to be strong and oscillating, it needs to have a wind response. And the wind response has to be zonal winds that kick off the ocean waves. And the wind doesn't just come out of nowhere, it has to be organized by the atmosphere. And the organization of the atmosphere isn't really considered in any of the ENSO theories. The winds are just considered slave to the SST in a very simplistic way. And I think they are neglecting that. And I have now some experiments that I do with a PhD student that actually shows that it's really the atmosphere that can do a lot of things in ENSO that are neglected in the theory, I think.
Okay, very quickly.
Actually, you already partly answered my questions. So, I was going to ask what the Walker circulation looked like in your twin.
Yeah, so in the twin, basically what happens is you have one heat source where there's an El Nino. You have lots of heat pumped into the atmosphere that leads to convection. And at the same time, you have a La Nina that has a heat sink, and then it goes down. So you can imagine when it goes up at one point at the equator and it goes down at the other equator.
So that was what I was imagining.
Like this, right?
So what would happen if you had 3 Pacifics?
I do have it.
Oh.
3 Pacifics, here it is. So if you have 3 equal size, you have 3 equal ENSOs. They are out of phase by 120 degrees, so you can try to imagine that, what it means in a cycle. And they have this interesting relationship, right? When you have an ENSO in the middle, you have the other one, an El Nino in the middle, you have decaying or developing La Nina, and then the other one is so it kind of moves westward in time.
Very nice, thank you.
But then if the center one gets bigger and bigger, you can see the variability gets weaker, but it gets less weaker in the center one than in the other ones, which makes the middle one dominant, the big one.